Hello, everybody. We're going to finish up our unit on chemical reactions today. We're going to talk about symbology in chemical reaction types, and predicting products. So before we get started, let me remove my image so we have more room, and actually we can see Homer eating a donut. So first thing we need to talk about is symbology. The symbology of that is in a chemical reaction equation. It tells you things like the state of the reactants and the products, the physical state. It also tells you conditions that may be necessary to cause the chemical reaction to occur. So, as an example, here, let me get my highlighter. Here we have a very common chemical reaction that you could actually try out at home. If you take baking soda, sodium bicarbonate, baking soda, and you add it to acetic acid, which is the vinegar solution that you have at home in the kitchen, if you mix these together, you're going to get a bubbly reaction that will produce carbon dioxide, water, and sodium acetate. Now, in a chemical reaction, you write down the formulas for these materials. For sodium bicarbonate, here it is, and then you see this little s in parentheses, this lowercase s. That means at room temperature, it's a solid. Then you have the plus sign. That means you're going to mix the sodium bicarbonate with vinegar. So this is vinegar, and there's this AQ in parentheses, lowercase aq. That means it's a water solution of vinegar. And in the vinegar that you have at home, it's roughly about 5% acetic acid and 95% water. You mix these together and you have an arrow. That means that the reaction is occurring. You're going from what you start with to what you end up with. And during that process, the molecules and the ionic compounds, they're pulling apart. The atoms are pulling apart, and then they're coming back together in a new substances. You produce CO2, carbon dioxide, and notice that there's a little lowercase g in parentheses. That means that the state of this material is a gas. And then you produce some water in this reaction, and that's indicated by a little lowercase l in parentheses, and sodium acetate. And this sodium acetate is in the water. It's dissolved in the water, indicated by the AQ, an aqueous solution. Okay, so sometimes you might even see a double arrow. What that means is that you have a chemical reaction that is reversible. And depending on the conditions that this reaction might be occurring in, you can either push the reaction in the forward direction or in the reverse direction. Things that you can change, for example, would be the temperature and the pressure, the heat input. If you put in heat or take away heat, you can push the reaction forward or backwards. Another thing you can do is you can put in more material of one of the components or take away one of the components, and that might push the reaction forward and backwards. You might see this little delta. What that means is that in order for the reaction to occur, you have to add some kind of a heat effect, either to heat them up, and typically when we heat up reactions, that will speed them up. Another thing you might see is a formula that is over the arrow, and this formula here, PD, that is palladium. PD is palladium. It's the element palladium. Palladium is used in catalytic converters in the exhaust system of cars. And they put it in there because they want to speed up the reaction of burning the hydrocarbons. So when the car engine burns gasoline, often it's the case that you will have some unwanted gases like nitrogen gases and sulfur gases, and there's still some leftover carbon, completely reacted carbon compounds. So they put this in what we call a catalytic converter, and it cleans up the exhaust stream of the car. And this had a tremendous benefit when these catalytic converters were introduced in the 1970s. They had a tremendous benefit in cleaning up the atmosphere, particularly in big cities. Okay, so now we're going to talk about types of chemical reactions. The first one we're going to talk about is combustion. Combustion means burning. So if you take what we call a hydrocarbon, which means a material that contains both hydrogen and carbon, and it might also contain oxygen, but here's a material, a hydrocarbon, and if you burn that, you are doing a combustion reaction. What happens, so for example, if we have methane, if you take methane, which is one of the gases that might be in your barbecue gas or coming out of your stove, if you take that and you burn it, and you will always burn it with oxygen, you will always combine it with oxygen, you will produce carbon dioxide and water. Now, there's something that I want you to notice in combustion. You will always have some type of a hydrocarbon. You will always have oxygen as one of the reactants, and you will always have carbon dioxide and water as your products. So notice that none of these are balanced. So why don't we take one of these and just balance it quickly? Why don't we do this sugar reaction? So here's a sugar reaction. This is what happens inside the body. For example, you eat sugar, either fruit sugar called fructose or cane sugar, sucrose, like a donut, right? It has a lot of sugar. This is what your body is going to do to digest it. It's going to take the sugar molecule, it's going to combine it with oxygen, and then it's going to react to produce carbon dioxide and water. So let's balance this really quick. I wonder if I can do it by just looking at it. I always like to start with the hydrogens. There's 12 hydrogens on the left. So on the right with this water, that's where the hydrogen is. What times 2 equals 12? 6. Okay. Let's go to the carbon. Let's do the oxygen last, because oxygen is by itself here on the reactant side. And whatever coefficient we put in front of this oxygen is not going to affect other things. So let's do the carbon. There's 6 carbons on the left. Let's put a 6 here. Now there's 6 carbons on the right. Okay, so the carbon is balanced. Now finally the oxygen, we have 6 times 2 in the carbon dioxide. That's 12 oxygens plus the 6 from the water. 12 plus 6 is 18. We have 18, we need 18 oxygens on the left. Right now we have 6 plus 2 equals 8. So I don't want to change the water or the sugar molecule. So we need 18. 18 minus 6 is 12. What times 2 equals 12? A 6. So there we have it. We have 6 times 2 equals 12, plus 6 is 18 on the left. 6 times 2 equals 12, plus 6 equals 18 oxygens on the right. Okay, now let's try to predict what reaction is going to happen. Well, it's easy with combustion reactions because you know that always the products that you will have in a combustion is CO2 and H2O, right? So you should always be able to recognize a combustion reaction. It's a hydrocarbon reacting with oxygen to produce CO2, carbon dioxide, plus H2O. Okay, the next type of reaction that we want to talk about is called a synthesis. In this type of reaction, you have two different substances combining to form one substance. So two different things are coming together to form one. Here's some examples. Magnesium, the magnesium atom, or 1 part magnesium, will react with 1 part oxygen to form magnesium oxide. To balance this, I would put a 2 there and a 2 there. 2 parts magnesium, 1 part oxygen will make 2 parts magnesium oxide. Here's another one. This is called the rust reaction. This is rust. So iron and steel. Iron will react with oxygen in the air to produce rust. Let me see, how do I balance this? 2 and a 3. I'm going to put a 2 there. 2 there. 4 here. 2 times 3 is 6, so I need to put a 3 there. Okay. Here we have the reverse of combustion right here. This is the reverse of combustion. And what is the reverse of combustion? What's the reverse? What's the reverse of respiration? We call this combustion. We might, in living things, we also might call this respiration. Right? When it goes in the forward direction. But what is it called when it goes in the reverse direction? Do you remember? Well, what you're going to learn in biology next year, this is called photosynthesis. Right? When it goes in the reverse direction, it's called photosynthesis. And this is what's going on in plants. So this is a very good reaction for animals that breathe air to make CO2. The plants are in the process of breathing CO2 to make oxygen. By the way, on this side, you need to put in the sun, right? Because in order for photosynthesis to occur, you need an energy source, and of course, that's from the sun. Okay, so synthesis reaction. To predict this, you really would have to go to the internet and look it up, right? So in some way, you do know that when these do come together, they're going to be in the form of one product because it's synthesis, right? So however that will look, it'll be just one product. Sulfur trioxide plus H2O. I'm not sure, I'd have to look it up, but this one I know. This one right here I know. And if you take nitrogen gas and hydrogen gas under certain conditions, you can make ammonia. Okay, this is a very important reaction. And the reason that is that using this reaction, we can just take nitrogen from the air and we can make ammonia, which is fertilizer. So this reaction here, when we figured out how to do that, because it's very difficult to break down the nitrogen from the air, when we did finally figure out how to do that, we were able to make enough fertilizer to feed more people. So you will notice, and this is at the start of the 20th century, when we figured out how to do this, the population of the world skyrocketed because all of a sudden we could have agriculture that could feed a lot of people. The next type of reaction is the opposite of synthesis. It's called decomposition. right? You just take synthesis and just reverse it. So decomposition, synthesis is just the opposite. A plus B goes to AB, right? So here's some examples of some decompositions. You have one thing on the left, one formula, and it splits apart into two or more different things. Okay, are all these balanced? It looks like a lot of these are balanced. Na2, yeah, that's interesting. What about this last one here? No, it's not. So we have 3 oxygens on the left, 2 on the right. The lowest common multiple between 3 and 2 is 6. So I'm going to put a 3 here. I'm going to put a 2 here. And then I have to put a 2 here, and it's balanced. So notice when I say it starts out as one thing and it ends up as 2 things, what I really mean is it starts out as one substance and it ends up as 2 substances, because there's not one part here, there's 2 parts. 2 parts of this potassium chlorate will make 2 parts of potassium chloride and 3 parts oxygen. Now, even though you're starting out with 2 parts and you're ending up with 5 parts of 2 different things, it's still called a decomposition, because you start with one substance, you end up with more than one substance. Okay, now we're talking about single displacement. The idea here, is that you will start out with one substance and another substance, and there will be a rearrangement. One part of one substance will attach itself to the other substance. So basically there's a trade. So this A here, starts out with the X, but then it loses the X to the Y. So that X trades places, is displaced to the Y. You can think of that as the Y going in and grabbing the X from the A. Single displacement. You might also see this as single replacement. Okay, so here's some examples. If you take copper and add it to, so this will be solid. If you take copper and add it to a gold nitrate solution, this is aqueous. I'm sorry, silver nitrate. Ag is silver. That will kick the silver out of solution, and you will get a solution of copper nitrate. So this first reaction is kind of interesting because it's a way to remove silver, which is a precious metal, from a dissolved state, right? Okay, here's another one. And notice also that you have a metal. One metal, copper, is displacing the silver, another metal, silver. Here's another one, calcium. If you take calcium metal, here's solid. You put it into water, which is liquid. You can produce calcium hydroxide, which would be an aqueous solution, and hydrogen gas. So here's a way to make hydrogen gas if you need hydrogen gas. Just find some calcium metal and you can make hydrogen gas. This next one is kind of interesting because bromine, instead of being a metal, it's a non-metal. Right? So you can actually you can start, instead of starting with a metal for this displacement reaction, you can actually also start with a nonmetal. Okay, so we know there's going to be a displacement. So the oxygen is going to trade places. So why don't we write zinc? The zinc is going to go from the sulfur to the oxygen. I'm sorry, the sulfur is going to go to the oxygen. So gas and solid. Okay, iron, again, it's going to trade places. What's going to happen when you do this? Well, iron chloride in some configuration. And hydrogen gas. And again, I am just predicting this. In order to make sure that I did it right, I would do a Google search just to make sure. There's also a double displacement. In a double displacement, the reactions, you have a compound that has two different parts and another compound that has two different parts, and they trade places. So I'm going to fix this up here just really quick. That should be a B. All right, two parts. So these are going to trade places. Right, these will trade places. It's called a double displacement. Here's an example. Notice that we start out with HCl, hydrochloric acid. We start out and we're mixing it with a solution of sodium hydroxide. If you do that reaction, the chloride will grab onto the sodium and the hydrogen will grab onto the hydroxide to form water and sodium chloride. Okay, let's try another one to try to figure this out. Okay, we have potassium iodide and we have lead nitrate. Now look at the products. We have lead iodide. So the lead and the iodide are going to grab onto each other. And the potassium and the nitrate are going to grab onto each other. So if you do this reaction, what will happen is there will be a trading of places, and you'll get lead iodide come out as a solid, and the potassium nitrate will stay in solution. So this is an interesting reaction because this is a way to get lead, dissolved lead, out of water, which can be useful considering that lead is very toxic. But again, double displacement, you have two, and notice that these displacement reactions, they always involve ionic materials. So the potassium iodide, the lead nitrate, there's a switch of the ions between the two, and they trade places. They displace each other. Okay, so what about this? Let's try to predict the results. So we know that this part of the ionic material will trade places. So the nitrate will trade places with the sulfur, with the sulfide. So we'll have lead, we'll get the sulfur, and we'll have the potassium, we'll get the nitrate. Okay, then you have to make sure that the charges balance. And I know that the lead has a +2, the sulfide has a -2, so that's a legitimate compound. And I know that the potassium ion has a +1, and the nitrate has a -1, so that's a legitimate compound. Again, just to make sure, you can go to the internet and look it up, or the chemical handbook. Okay, so that's a summary of all of the types of reactions. There's 5 of them. There, and again, just really quickly, there is the combustion, always makes water and carbon dioxide. There's synthesis. 2 substances are coming together to make 1 substance. And when I say 2 and 1, I don't mean actual numbers or parts of materials. It could be 5 parts, for example, 2 parts hydrogen gas, 1 part oxygen will make 2 parts water, H2O. There's opposite of synthesis is decomposition, right? You have 1 substance will split apart to make 2 or more substances, decomposition. And then you have the displacement reactions, single displacement and double displacement. So what we have here is, in a displacement reaction, will something displace another thing from a reaction, and that's called the activity series. So using this, you can predict whether a reaction will occur. So things that are higher on the list, are more active, we call it active, than things that are lower on the list. So things that are higher on the list, they tend to be combined with other things in a chemical compound because they're very active. Things that are low on the list, they tend not to be combined with other things because they're fairly unreactive. And that's why we call these last 2, it's silver and gold, that's why we call them noble metals. They tend not to react with anything. So that's the activity series. You can use this to predict if you have competing reactions. You can use it to predict whether something will react or not. So for example, okay, we have, let's just pick one. Let's pick this one. So we have silver. Silver nitrate is reacting with sodium chloride. Will that reaction occur? Well, look, sodium is much higher on the list than silver. So yes, that reaction will occur because sodium is much more active. Okay, as a review, let's try to predict what type of reactions these are. The first one, let me see, we have 2 substances coming together to make 1. Well, that's easy, that's synthesis. And I'm going to balance this. Let me see, we got 2 H's on the left. We only have 1 on the right, so I'll put a 2 there. Now we have 2 chlorines on the left and we have 2 on the right. So again, notice that this is 1 part hydrogen. So you can take 1 cup of hydrogen. Well, how much chlorine gas do you need? 1 cup of chlorine gas. Actually, it'd be better to talk about liters, right? Because these are gases. So 1 part hydrogen, 1 part chlorine will make 2 parts hydrogen chloride gas. The next one, we have aluminum, and we're putting it into a solution of copper chloride. Will a reaction, well, first of all, what type of reaction it is? Well, the aluminum goes in and it steals the chloride, right? So this is called a single displacement. Okay, so the aluminum steals the chloride from the copper. The question is, will this reaction occur? Well, let's go back to the activity table, will aluminum displace copper? Well, here's aluminum and here's copper. So yes, it will. Aluminum will displace copper because it's more active than copper. Let me get back to there. There we go. Okay. So if you take aluminum solid, like a powdered aluminum, and you throw it into an aqueous solution of copper chloride, you are going to cause the copper to fall out of solution as a solid. We call this a precipitate. When something that is dissolved falls out of solution as a solid, it's called a precipitate. What's the next one now? Well, this is interesting. We have a carbon hydrogen compound. It's reacting with oxygen to produce carbon dioxide and water, and that's easy. That's combustion. Okay, this is combustion, and in fact, this is called octane. This molecule with 8 carbons and all hydrogens is called octane. We also call that gasoline. Okay. The last one, here we have a double displacement. Or the fourth one. Right, so here we can see that we have the potassium ion is going to trade places with the lead cation. The iodide anion is going to trade places with the nitrate anion. Okay, and then finally we have what's the opposite of synthesis? What's the opposite of a synthesis? Decomposition. Okay, let me write that there and then we'll end this. So you can see that these are the 5 basic types of reactions. These reactions, they basically account for 99% of the reactions in the universe. So you just have to learn 5 and you know a lot about chemical reactions. So I'll see you next time. Take care, everybody.